Hi, I'm Matt.
I'm Fernando.
And we are Iron Age Audioworks. Today we're going to be doing a little demo of testing op amps. We made up a batch and we thought, hey, this would be a good time to talk about it a little bit. This is our op amp test setup. We have an op amp test jig that we got from Five Fish Audio. It's really configurable. You can use either socketed or discrete op amps in the 2520 footprint. You can pick your output load resistor. It's got BNC connectors for the outputs and the inputs, and then using all these jumpers you can do inverting or non-inverting, pick your gain, that kind of thing. This is just a simple power supply, a bipolar power supply, and then over here we've got a terminal block, and we have a multimeter set up in series with that so we can actually measure the amperage. It's good to kind of see what's going on, and when you're doing a different op amp, see how much power consumption each one has. This is our power transformer. So we've just got it here in a box for safety reasons and a little switch with a fuse. So we turn it on. You see the inrush current as the caps fill and then it settles out. This power supply takes about 15 milliamps. And so you can see this op amp's taking 7 or something quiescent current just hanging out there. So what we've got here, these are some in DOA Iron Age. We just soldered these up. These are based on the Neumann OA10 op amp. They're a little 12 transistor, really cool, really thick, warm sound. And so we're ready to test. The rest of the setup here, we've just got a simple interface that's doing the inputs and the outputs into the op amp test jig, and then that's running to the computer. And so over here what we're running is Rightmark Audio Analyzer. Today we're going to do some testing with Rightmark Audio Analyzer. It's a free tool you can download online. It works with almost any interface or sound card, and it works with Windows or ASIO drivers. So once you get your playback and recording device or your interface set up and configured, you can see down here there are tests and options. So you can set up various things about the sound card, whether you're doing mono or stereo testing, and you can select which test you're going to do. Today we're going to do frequency response, noise, and total harmonic distortion. Then you come down here to your adjust playback and recording. So here's the adjusting level screen. You see your send and return levels and then a spectrum of the test tone that you're sending out. So we're sending out a 1K. The levels here are shown at minus 8.3 decibels. That's because our particular interface has about a 1 dB insertion loss to send and another one to return. So we're losing about 2 dB on the round trip, and then because we're sending a balanced signal into an op amp in an unbalanced configuration, so it's not set up as a balanced receiver, we're losing another 6 dB on the level. So 8.3 is right where it should be. That decibel on RMAA is shown at decibels full scale, so that's based off of your particular interface's 0 dBFS reference point. This particular interface is referenced at plus 24 dBu is 0. So this signal is actually going in at minus 8.3 from there, which is roughly 15 dBu or about 13 volts peak to peak. So once everything looks good, and it does, we start our test. Have a small speaker hooked up so we can kind of hear what's going on. Sends various test tones and white noise for the different tests that it then analyzes what comes back. When the testing is done, you can pick the slot that you're going to record it to. We'll just say test JDOA 1. Okay, so it loads it into the test cell, and you can compare multiple test runs, which we'll do in a minute. Here you can see the frequency response, noise level, and THD numbers that came back. And then you can right-click on each one to see detailed reports. So if we click Show Graph and Details, it gives us a frequency response from 40 Hz to 15K or 20 to 20K. And you can see that in the 20 to 20K, we're basically within 0.13 dB. If we look carefully at our graph, we see that the graph is very, very flat to below 10 Hz and then well above 30K. This is actually from our interface. So the interface has a low-pass filter that it's using to filter out noise and radio frequency stuff, anything above the audible spectrum. So this is part of the measurement error, you would say. So most op amps have plenty of open loop gain and slew rate to reproduce signals even well above the audible spectrum without having a frequency roll off. If you were sending a lot of gain through this, maybe 40 or 60 dB, some op amps might start to show a non-flat frequency response where the upper end of the audio spectrum may start to roll off prematurely. But in this case, we're not, so that means this op amp is faithfully reproducing 20K at plus 15 dBu. That's good. That's what we would expect. Then we see noise level. So this is our 60 hertz from our power. If you were in a place that runs on 50 hertz, like the UK or Europe, you would see this at 50. And then we see harmonics of the power, so at 180 and 300 and so forth. And then up here, this area around 10K, that's actually related to our specific interface. So that's our noise floor. That has to do with the impedance and the fact that we're running unbalanced out of an IC balanced interface. And then if we look at the total harmonic distortion graph, now we see our noise floor, and superimposed on that we see the test tone at 1K that was sent in. So we see our first harmonic here around minus 55 dB, our second harmonic at 3K down at minus maybe 95, and then you can probably see our third, but the fourth is hidden by the noise floor. So this is our THD response for the op amp. Anything below that the op amp is doing is covered by the noise floor of the interface. So at plus 15 dBu, this op amp into a, I think it's set to 10K, is making a THD of less than 0.01%, which is a pretty typical response for an op amp. So now we'll change the op amp out, turn the power off, disconnect it, grab it carefully by the PCB, and wiggle it out. So sometimes when you're installing new op amps for the first time, these sockets can actually be really difficult. So we thought we'd show what we do here. I've seen suggestions to use a paper clip or something to break them in. We just took a bare PCB and soldered the pins into it. And then that's actually a really easy way. You can line it up, and then because it's nice and flat now, you can just press it on there and break in the sockets that way. And again, to remove these socketed op amps, you just wiggle them out. So now we'll change to a different op amp. This is the first one was an M2. This is an N DOA. So we just line it up, slowly press it back in, plug in the power, turn it on, and now we'll repeat the test. And see if we can measure any noteworthy differences between them. Okay, so now we're going to test the NDOA. We start our playback and recording. And we have our same levels. Everything looks good. Right away you can see that we're going to see some differences in distortion just because on our spectrum we have much higher peaks in the spectrum here of the harmonics. But we'll go ahead and run the test. And we'll load this one up. Okay, so we have very similar noise levels, very similar frequency response, and that's to be expected. Both of these have plenty of open loop gain to meet the 20K ceiling that we're measuring at with plus 15 dBu, and right now they're set up as a buffer, so there's no gain being asked of the op amp. So again, that's what we would expect for a working op amp. But you see we have a very different total harmonic distortion number, 0.03 for the Neumann at plus 15, and then when we look at that you can see the Neumann is much, much higher. So that's the same spectrum that we got back when we were doing our initial testing. So not only is it higher, if you remember the M2 was way down around 90 for the second harmonic, but also you see the odd distribution is not regular. Our second and third harmonics, or our harmonics at 2K and 3K, are almost equal. So this is a good example of a harmonic distortion that's going to have some odd and even content in it. So that may sound a little brighter, may sound a little, if you get too much, it'll sound maybe gritty or harsh. And that's because the Neumann doesn't have as much output drive capacity. It can't drive as much amperage into a load. And so here it's actually in class AB on the output. And we'll test one more to compare. Swap the op amp out. Now we'll test the Jensen 918. Run the same test again. Our levels look good, and again you can see very different distortion profile already. And for the tests that we're doing, that should be the difference that you see. Different op amps may have different power supply rejection ratios, so they may be a little bit quieter. But generally, at the levels we're testing, they're going to be very comparable. I mean, that's basically within measurement error. So the total harmonic distortion of the Jensen style is quite a bit lower, and you can see really nice here superimposed, the Jensen on top and the Neumann behind. And so very comparable noise floors. None of them are doing a particularly better or worse job at changing that, and that's because the op amp is quieter than the interface. But then you can see the harmonic distortion from the Neumann style, the NDOA, is quite a bit higher on all the harmonics than the Jensen, which has this shape there. Okay, so let's do one more test. I changed the load resistor and I put the Neumann back in. So now we're going to see if the total harmonic distortion on the NDOA changes, right? So it will, and we can compare those two results. You can kind of see an example of what you might get in different circuits, even with the same op amp or different op amps. So here we have the NDOA with a 10K. So we have an order of magnitude difference between the two tests, and that's going to be solely related to the load resistor. So here we have a higher harmonic distortion, and that's coming from crossover distortion when the Neumann is pushing the amperage class AB on the output stage. So since you have a 600 ohm load resistor, it's moving more current at the same voltage level. When you switch over to the 10K, it's probably either completely class A or transitioning from class A to class AB, and that's why you have a much higher even harmonic versus odd harmonic distribution, whereas in class AB, the odd harmonic level has come up quite a bit. So you can't test everything you might want to test for an op amp using RMAA, but you can see some meaningful results, and different circuits will give you different results, especially when you're talking about something like the load that the op amp is pushing into it at a higher level, like plus 15 dBE.